Hello, in today's mathematics video assignment, we will be talking about linear approximations of nonlinear models and the Taylor series. Today, we will start off with the linear approximations of nonlinear models. Now, what is a linear approximation of nonlinear models? This is a method in which a general function is approximated by a linear function. Now, you would ask yourself, why is this topic relevant? Linear approximations and linearization makes it possible to use tools for studying linear systems to analyze the behavior of a nonlinear function near a given point. Now, what are some primary applications in which this can be used? This is used in the method of finite differences to produce first-order methods for solving or approximately solutions to equations. This is also applied in Euler's method, which is used to approximate solutions to a couple of first-order differential equations. This is also used for decision rules in microeconomics, which are related to the strategy in game theory. Also, in pendulum, the period of oscillation, in which a linear approximation can be used to calculate the period of a pendulum, given that the amplitude is limited to a small angle. Also, and finally, this can also be used in electrical resistivity, varies with temperature. If, however, the temperature range is minimal, a linear approximation can also be applied. The next topic we will be talking about in the mathematics video assignment is the Taylor series. Now, what is the Taylor series? The Taylor series is a series expansion of a function about a point. A one-dimensional Taylor series is an expansion of a real function f of x about a point x equals a, which is given by this equation right here. Now, if a equals 0, in this case, the expansion is known as the Maclaurin series. Now, you would ask yourself, why is this topic relevant? Before the age of electronic calculators, mathematicians studied these algorithms in order to approximate these functions manually. Taylor series, named after English mathematician Brooke Taylor, is one such way of making these approximations. The strength of the Taylor series is its ability to approximate certain functions that cannot otherwise be calculated. This has helped mathematicians approximate the values of important irrational constants such as pi and e. Now, some primary applications in which this is used. This is used in computer science, calculus, physics, among many others, or in any higher level of mathematics. Now, this is used to create an estimate or guess of what a function looks like. If a point is chosen on the coordinate plane, then it is possible to guess what a function will look like in the area around that point. This is done by taking the derivatives of the function and adding them all together. The idea is that it is possible to add the infinite number of derivatives and come up with a single finite sum.
Example here, f of x equals ln of x at the point x equals to 2. We start by differentiating the formula f of x equals ln of x. So the first derivative of ln of x equals 1 over x. In order to make it easier for us to plug into the formula, and in order to make it easier for you guys to actually see the generalization, 1 over x equals to x to the power of negative 1. The second derivative is then negative 1 times x to the negative 2, as seen by normal simple differentiation. The third derivative is therefore 2 times x to the negative 3. And we can now already see a sort of pattern going on. When going to the fourth derivative, it is negative 3 times 2 times x to the negative 4. And the fifth one, it will be 4 times 3 times 2 times x to the negative 5. As we can see, as we are in the third, fourth, and fifth derivative, the x power has the same number as the derivative we are currently at. Furthermore, we can also see is as we are on the third derivative, and the fourth and the fifth, we keep on adding, we keep on multiplying by one number less than the derivative we're currently at. So at the fourth derivative, the biggest multiplier is 3. At the fifth, the biggest multiplier is 4. After having differentiated the actual equation, f of x equals ln of x, we plug in our value, which is 2. So we plug in 2 into f of x and get ln of 2. We plug in 2 into the first derivative of f of x and get a half. we carry on doing this, and as we can see here as well, basically all of the exponents here are corresponding with the number of derivatives we are currently at. So the fourth derivative, we have an exponent of 4, and so on and so forth. Here we have now multiplied out the actual values, -3 times 2, as well as 4 times 3 times 2, in order to then plug it onto the formula. The final step is actually plugging it into the formula, which we saw up here. And to do this is very simple. All we need to do is plug in the equations, or the actual the equations we got from plugging in the number 2. So at the end, f of x would be ln of 2 times a half, since this is what we have to do here as well. Okay, third derivative times x minus 2 over 1 factorial plus minus 1 times a half to the power of 2 times x minus 2 to the power of 2 over 2 factorial. And here again we can clearly see the corresponding equations. The second factorial, the second derivative has a factorial of 2, the third derivative has a factorial of 3, and so on and so forth. So finally, the main point to actually realize is that if we are at the fourth factorial, for example, the fourth derivative, we have an exponent of 4, we have a factorial of 4, and it is just a summation of different derivatives in order to approximate our function.
Okay, so using Desmos, we can actually see what the Taylor polynomials help us to do. So here we have in red the line y equals ln of x, or the function y equals ln of x. If I add the Taylor polynomials, using the general formula seen here on the left, we have the blue line, which if I increase this using this ledger, reaching from 1 to 25 for the value of a, we can actually see how the Taylor polynomials help us to model the function y equals ln of x. So the higher a goes, the more sums within the Taylor polynomial, the closer the approximation to the actual function we have. And this can be perfectly seen through Desmos, as portrayed here, and it's basically the most crucial part about Taylor polynomials.
Alright, so this is the example for the linear approximation of nonlinear models. And what we have here is the green function, which is x squared, and then this red line is the secant line, which is used to approximate the slope of x squared, or the function in question. And now in order to do so, we have the delta x, this value, which is the distance between this point here on the secant line, the two intersect points of the secant line on the function x squared. And so you have the horizontal distance between these 2 points, which is delta x. In this case, it is equal to 1. And then you have the vertical difference between these 2 points. In this case, this is delta y. This is delta y, and in this case, this is 1.660. And in order to find the slope, the formula is delta y over delta x. So you just plug in those values, and then you have the slope of the function. And now here, this is to approximate. Now, as you decrease these values, for example, I'll change delta x from from 1 to 0.1. The values get more accurate, and as you add more zeros, as you can see, the value over here keeps on getting to a more accurate state. And finally, final example, it goes on to 0.601 and keeps getting more and more precise. So this shows that as you decrease the value of delta x on the linear approximation of nonlinear models, the secant line becomes the intersection points of the secant line become closer together, therefore heightening the precision of the approximation.